Professor Elad Alon is a professor of ECS at University of California, Berkeley, as well as the co-director of BWRC. He is also co-founder and chief scientist at Blue Cheetah Analog Design, which is commercializing generator technologies in order to enable analog mixed-signal solutions at lower barriers of entry. He's had advisory, consulting, and visiting positions as pretty much every company in North America, including Higher Labs, Voltage, Lance Semiconductor, Cadence, Xilinx, Velocity, Particles, Intel, and AMD, Rambus, HP, and IBM. He's won several awards, including the IBM Faculty Award, the Hellman Family Faculty Award, the UC Berkeley Electrical Engineering Outstanding Award twice, and has co-authored papers that received the Best Paper Award at CICC, VLSI, multiple times. So please welcome Professor Elad Alon.
Thank you. Great, so thanks very much for the introduction. Let me make sure my microphone is on. There we go. Okay, so thanks again for the introduction. I guess you guys put me here at the end so that nobody else can counter any argument that I make. But nonetheless, actually, I think the directions have been quite interesting in terms of the different evolutions we're seeing, and I'm going to say some more about that. I will perhaps not be quite as, let's say, dogmatic in terms of saying it has to be X or Y, but certainly I will make the case for what I think is, what are the cases where mixed signal stuff really does actually make a lot of sense, even still today at the 5612 gig generation. And now we'll see if we can actually get the slides to advance. Come on. Oh, that seems to be stuck. There we go. Okay, now it's alive. Okay, so I'm sure you guys have heard a lot about this all day, but I want to just sort of cast it, in one particular light to make sure we're on the same page. Which is, if we just kind of globally look at what is the SerDes problem, really in an overall nutshell. To zero order every 4 years or so, we're saying that we would like to increase the throughput by about a factor of 2. And today, indeed, 56/112 per lane is about where people are kind of starting to roll things out. Now, having said that, for better or for worse, the system architects don't really change the power budget for the SerDes any, because at the end of the day, that's just moving data around. You probably actually want to do something useful with the data. And so that means that from an energy efficiency standpoint, you basically have to improve, right? If you're going to double the rate and keep the power constant, your picojoule per bit has to go down by that same factor of 2. And on top of that, of course, most of the system vendors would love to not have to actually upgrade their physical channels along with this increase in the data rate. Now, in reality, upgrades are kind of happening continuously, and in fact, I'd say that it's kind of become somewhat more lockstep of channels moving along with the data rates that you're targeting. But nonetheless, this is indeed in a sort of direction that people would like to be able to meet if they can. And the last thing is, not to sort of pile on doom and gloom, but as I think everyone knows pretty well, the process technologies themselves are not advancing in the way they used to, and that you're not just getting raw device performance that's kind of going right along with the data rates you want. And in fact, it's maybe even either tapering off or in some cases getting slower. And so you kind of have to do all of these things all at once, which is get the thing to run faster, make it burn lower power, and do that with increasingly not really much help from the technology side. So kind of looking back a little bit, it was kind of interesting for me to sort of observe how things evolved for a period of time. And I'm going to kind of argue that for probably about a decade or so, I think that there was what I'm going to call a quote-unquote golden architecture that many SerDes were following and many different companies kind of all independently converged on. Now, this is not to say that this is the only way to do it. This is not to say that it's gold in terms of it being better than anything else. I'm just sort of casting this more in a historical light of there was this kind of period of similarity where almost everyone was taking a very similar approach for a while. And so the genesis of this, I think, was right around 2005. There was a few papers at VLSI that all sort of came out and followed what I'm going to call being the first representatives of this golden architecture. And again, if you sort of look over the years, and I just took a very small snapshot of this. Folks from Rambus, folks from Xilinx, folks from Broadcom, folks from Intel, in fact, many other companies, all ended up having architectures that looked quite similar to essentially what I'm going to describe here. So they were all essentially relying on NRZ signaling. They all had some amount of TX feed-forward equalization. They ended up kind of converging on all having some reasonable amount of received CTLE, and they all had varying degrees of decision feedback equalization. They all essentially relied pretty much, I think, almost uniformly on sine-sine LMS-based adaptive equalization. And almost everybody was relying on 2x oversampling CDR. Exactly when this quote-unquote stopped is now much more arguable. But there was probably about a good decade or so where all of the Link's papers kind of had the same flavor to them. And I shouldn't say all, but many of them, sort of had this similar characteristic. So obviously, as was set up from the very get-go, I'm sure Johan, unfortunately, I couldn't be here, but I'm sure he gave a great talk about ADC-based SerDes and, told you indeed how, the world should now be ADC-based. And indeed, that's gained a lot of traction in the 56 gig to 112 gig generation. So what I'm going to try and aim and do in this talk is give you a few insights into, first of all, why is it that I think analog mixed signal was preferred for kind of this, quote-unquote Goldman architecture for about a decade or so. Why even today you might choose an ADC plus digital versus an analog implementation, or in fact, probably in reality, some mix between them is, in some cases, actually going to be really your best bet. And then finally, just give you a few kind of insights into what I think are the key techniques you really want to adopt for the analog mixed signal portion of things, which, by the way, side hint, those ADC things actually have a lot of analog mixed signal stuff in them, and so you have to get those right if you actually want that to succeed too. Okay, so the way I'm going to sort of structure all that is first I'm going to do sort of a brief review of just where does power actually go in various portions of the SerDes circuits. What are some of the implications of that on both the circuit implementations as well as the overall architecture? Give you a little bit more sort of information from a 60 gigabit per second, 65 nanometer design that came from my group about 2 years ago now, and then just sort of give you some overall conclusions and let's say tips for the future from my perspective. So let's just start out with kind of, again, looking at where does power consumption really go in SerDes circuits. And in fact, I should make this even somewhat more general in that I think if we just start looking at where does power go in circuits in general and what are sort of the key factors that set your power dissipation, this is already going to give us a lot of insight into some of these questions that we brought up in the very beginning. So as a first step, if we just say, let's look at the digital components of our circuits. And, by the way, whether you're DSP or mixed signal, there's actually a lot of digital stuff, which is probably going to end up being a good chunk of your overall power. And there, hopefully everyone knows these kind of things quite well, right? If you kind of neglect the leakage in the crowbar current, which for a lot of the SerDes stuff we're doing is a reasonably good assumption, there's kind of this classic equation that probably everyone is familiar with, which is just, okay, my power is something like, some activity factor times the load capacitance times the supply voltage squared times the clock frequency. So the only other thing I want to add onto here, which I kind of highlighted in the slide, is I'm going to add this extra kind of term on the right, which may look a little bit funny at first. But what this is basically telling you is that if you try and push the speed of that circuit up too close to kind of the intrinsic speed of the inverters themselves, and as a reminder, there's an intrinsic speed because the transistors inside the inverter always have some parasitic capacitance. The bigger you make those transistors, the bigger the parasitic capacitance, and so there's kind of like this intrinsic speed limit that you hit. All this term over here on the right is telling you is that basically the closer you try and get your actual delay relative to sort of that intrinsic delay, the more power you're going to end up having to spend to really hit that type of thing. And again, this is kind of intuitive of, let's say half of your capacitance is just coming from your own inverters. Well, guess what? You're spending basically twice as much power as you would have otherwise had that capacitance not existed and that speed limit not existed. So the meta point here is that essentially, ideally speaking, you want to set that supply voltage based on how much throughput you actually need. Because at the end of the day, moving that supply around is kind of your knob for adjusting the delay. But at the end, also be careful that you're not trying to go too fast relative to what the process technology really constrains you to do. Because at some point you'll hit this sort of, if you look over here on the bottom right, there's kind of like this normalized inverter delay compared to the, kind of like intrinsic delay. Basically, if that term starts becoming too small, the whole thing goes off to infinity, and it's just saying you're driving all of your own capacitance to try and get this speed. And so obviously, you kind of fall off a cliff in terms of power consumption. Okay, so that was kind of like, obviously I took this really big hammer and I just said, the digital world all is an inverter, and this is my equation for all inverters. And, despite that being a really big hammer, it's actually not that bad of an approximation. So now I'm going to switch over to how much power do you have to spend on the analog side of things. And here, this discussion actually has to be a little bit more nuanced. The classic one that you'll see kind of, let's say from back 15, 20 years ago or so, is usually assuming that your analog circuits are actually limited by signal-to-noise ratio, or said another way, they're limited by dynamic range. And so you can actually come up with a similar equation, and the amount of power you have to spend is essentially some proportionality constant related to the noise in the transistors, times the actual signal-to-noise ratio, times kind of like intrinsic things like, Boltzmann's constant and temperature, times the bandwidth, times this kind of like normalizing thing that I have over here on the side, which is really just related to basically how big is your signal swing relative to kind of your linearity constrained behavior of the device, okay? And if you're not familiar with this stuff over here on the right, it's not really all that important. It's just kind of a small integer factor you have to be careful of. So kind of the only things you have allowed to play with here, right? Signal-to-noise ratio usually is limited by kind of your system application. Bandwidth, again, is limited by the system application. Boltzmann's constant and temperature, not a whole lot you can do about those. So kind of the only kind of thing you have left to play around with a little bit is indeed this kind of ratio of the actual signal swing compared to the maximum swing your devices can handle. But other than that, this kind of tells you fundamentally this is how much power you're going to burn. The other thing, which is again pointed out often when you look at these things and is really kind of the key point here, is that you typically are adding explicit load capacitance into these circuits to try and make sure you're hitting the signal to noise ratio constraint. And once you're doing that, every single time you want quote unquote an extra bit, that means an extra factor of 4 in signal to noise ratio, because unfortunately signal to noise is a power quantity, not a voltage quantity. And so that means you have to spend 4 times as much power to get back to sort of, to basically hit that particular constraint, okay? So, that's kind of this classic scaling thing that people say of, every bit in analog is a factor of 4, and in digital, that's much easier, it's just one more bit, right? Well, there's one quote-unquote side case that I want to point out here, because it turns out this side case is actually where most SerDes operate, okay? And that's where, well, what if I actually build my circuit, I add no explicit capacitance whatsoever, but just because of the capacitance that was there anyways, I actually have better SNR than I already needed, okay? Well, if I'm in that regime, now actually things change a little bit, and they turn out to look more similar to what that digital equation did earlier, okay? So now, the lower the capacitance is, the lower the power I get to burn. Essentially, there's some factor related to just kind of like the transconductance efficiency of my device. You can kind of think of this as like the closer to subthreshold you get, kind of the more current efficiency you get out, but obviously the more parasitic capacitance you'll pick up. And then essentially there's just a gain bandwidth term here, which is telling you obviously the higher the gain bandwidth you need, the more power you're going to spend. And then there's this factor over here on the right, which is again very similar. It's just saying if that gain bandwidth you're shooting for is getting too close to the intrinsic gain bandwidth, this gamma D here is just saying like the ratio of the gate to the drain capacitance. Again, just kind of some relatively constant number as a function of your process technology. Basically, all of this is saying that, gain bandwidth is sort of replacing frequency in some sense, but essentially the faster you want to go, the more power you're going to spend linearly. But once again, be careful to not go too fast relative to the process, because then things will blow up. Okay, because again, you can see the gain bandwidth basically is equal to something like your FT divided by that, capacitance ratio. You can spend infinite power, you can't actually implement it. Okay. So what's the point of all this? Well, as I was already hinting at a little bit earlier, if you're really working in the high dynamic range regime, right, where you really need very high signal to noise ratio / very high essentially dynamic range, then digital clearly is the winner, right? Because, for example, if I've already got 10 bits and I just need to add one more bit, which remember gives you a factor of 2 improvement in voltage precision, hey, that's like a 10% change in my power, right? Maybe a little bit more because of throughput, but to zero order about 10%. Whereas if I'm really operating kind of in the signal to noise ratio limited regime on the analog, now it's a factor of 4 just for that one stupid bit, right? Well, on the other hand, if I'm actually in this low dynamic range regime, which, this is a super rough order of magnitude, but ballpark around 5 to 6 bits or so. This is where, turns out, analog usually kind of just gives you that signal to noise ratio without even you really trying. And so there, it's really all about total capacitance. Right? So the name of the game is just whatever solution gives you lower capacitance, that's pretty much the one that's going to win in that case. And this is where actually, I think a lot of the motivation for the original golden architecture actually came from. Because if you sort of think about it, especially for things like just doing, multiplication by some, somewhat imprecise number and adding things together, which is what a lot of these equalizers are actually doing, well, I can do multiplies and adds really, really simply with a very small number of transistors in analog, whereas in the digital, even if I'm doing like 4 or 5 bits, just count the flops and pretty quickly you'll see why there's a lot more capacitance to do it in the digital domain than there is to actually do it in the analog mixed signal domain. So I'm going to argue that, not that I think everyone necessarily thought this all the way through, but I think this is really the strong motivation for why people were taking the approaches they were for such a long period of time. So the next question is, well, okay, so if I'm going to argue that this is why people took this approach in the golden age, did things really change? Have we really gotten to a regime where the dynamic range is now sufficiently high that we really should be switching into a digital implementation? So I'm going to play the classic, non-committal answer. In some applications, maybe. Okay, now let me clarify that a little bit further. So I think if you're really looking at a very long range, quite lossy but still smooth channel, maybe you're really starting to push into the regime where the analog front end actually needs a lot more than 5 or 6 bits of dynamic range. I'll point this out a little bit later. Just to be clear, 40 dB is like 6.5 bits. Okay, So it's still not obvious that you've actually fully crossed that boundary. But, let's be generous. Let's say indeed, there's something else going on. Maybe there are some applications where this really happens. I'm still going to argue, however, that almost all of the ADC plus DSP, sort of implementations that I see actually still have some reasonable amount of analog pre-processing happening inside of them for exactly the same reasons. So let me actually kind of walk through that a little bit. And so this is actually a paper taken, I think, from Johan's group directly from ICC, a little over a year ago. And so you can see, yeah, indeed, they've got this, 7-bit to 3-bit SAR ADC, but there's all these stages of, various forms of continuous time linear equalization sitting in front of them. And I don't know how they actually built those circuits, but let's pretend for the moment that, it's one of these source generated kind of structures. If I just go and I compute, analytically, how much power should it take to build these kinds of things in a reasonably representative, quote unquote, 16 nanometer generation process. So something like a supply voltage of, say, 0.8 volts, peak gain of about 2, a bandwidth of about 60 gigarads per second, which would correspond to something like a 28 gigasample per second design, load capacitance of about 10 femtofarads. All of this should take you about 274 microwatts for each one of those CTLE stages, okay? So the question is, well, all right, so let me compare that against what it would take to actually build the same functionality in the digital domain. So if I take the same 0.8 volts and I get the same net throughput, then it turns out kind of the effective capacitance you can afford to sort of make this the same amount of power in the digital domain will end up being about 15 femtofarads, okay? And to be clear, I'm giving you the ADC completely for free here, right? Not only am I giving you the ADC for free, I'm giving you the extra resolution you need in the ADC to not have linearity issues because of you not doing CTLE. I'm just giving that all to you completely for free. So I'm literally just comparing, analog function versus digital function, no other second order, sort of effects taken into account. So this is where we can get a little bit into, well, what's the smallest flip-flop you can actually build? But to zero order, I see things on the order of about maybe 2 to 3 femtofarads or so for each flip-flop from a kind of effective capacitance standpoint. And most of this, by the way, is just dominated by the clock load itself. And so the implication of this is that, if I wanted to essentially build the same CTLE function, which to be clear in the digital domain would be an IIR filter, right? Something that actually has feedback inside of it, then basically you can afford at most about 5 to 8 flip-flops in order to be actually better than the analog, okay? So if I've got even 2 7-bit numbers that I need to add together, that's already 14 flops, and then I need a result, so that maybe that's also 7 bits or 6 bits, but you can see pretty quickly why it is that this math, looks like the analog just wins, right? And so to be clear, there are some games you can play to try and improve things on the digital side. Particularly, you could say, well, I'm going to go and build a heavily parallelized implementation and then drop the power supply voltage and get better energy efficiency in the digital that way. To an extent, yes, but remember, this is an IIR structure, so it actually has a feedback loop in it. So that means there is an inherent latency constraint you have to meet. So there's kind of only so far you can play this trick. And in practice, again, I think, I'll just sort of point to the reality. I think this is why you start seeing most people do, especially CTLEs, sitting out in front of the ADC. Okay, so now that we've kind of gotten a little bit of a flavor of, where it is that I think kind of the key crux of making the decisions comes from, what I want to do is spend a little bit of time just talking about, okay, if I'm really going to try and optimize these mixed signal implementations, what does that mean about how I want to construct the overall SerDes architecture? So one important note here is that, most of the sort of discussion that I'm going to do specifically in terms of how you kind of balance out the equalization architecture is really going to be, specifically talking about things that do not have forward error correction. I will also mostly be talking about NRZ examples, but almost all of what I'm going to say is kind of independent of those two, let's say, design decisions, meaning almost everything I'm going to say is going to be equally valid even if you're doing a PAM4 design with forward error correction, okay? So the only real big difference between essentially, those 2 bits being flipped and what I'm going to say is just that, in particular, if you really are using substantial FEC, it'll just move you away from doing these longer multi-tap decision feedback equalizers, and instead you'll be doing longer feed-forward equalizers. Okay, but pretty much everything else is about the same. Okay, so from the equalization architecture standpoint, and again, this is mostly independent of whether you're choosing analog versus digital, obviously efficiency is going to drive very much what selection of components you're going to include, and what it is that you're going to try and use each of those components to actually tackle from the standpoint of various impairments introduced by the channel. So let's just assume for the sake of argument, this is kind of what your channel looks like. Typically speaking, the feed-forward equalization, again, with this caveat of not using sort of forward error correction, typically speaking, the feed-forward kind of stuff, meaning the stuff you put as TXFIR as well as anything that might be on the receive FFE, is mostly trying to deal with the precursor stuff, okay? And the reason for that is very simple. It's pretty hard to kind of get a good mimicking circuit that really creates this precursor sort of cancellation effect out of a continuous time linear equalizer. And obviously, if it's decision feedback, there's no way to get rid of stuff that's actually before your decision. So because of this, you're mostly using the feed-forward stuff to essentially deal with these with the precursor ISI. Once we're past the cursor, this is exactly where DFE is kind of intended to do its main job. But having said that, you don't really want to build super long DFEs, because kind of for much the same reason I said before, it turns out that flip-flops can actually be very much the dominant power cost of your DFE once you've done everything right. Because just keeping the data around that long can end up adding up fairly quickly. And so you typically want to use kind of a reasonably short, here I'm saying 3 to 5, what the actual number is obviously depends on your exact channel, but you want to try and keep the DFE itself reasonably short just so that the power overhead from the flip-flops themselves doesn't add up too quickly. Then finally, it turns out kind of what I'm going to call this so-called long tail type of response. This is dominantly what the CTLE is really going after. And the reason for this is just that, if I have something that's kind of like this long, slow RC roll-off that's perhaps, a couple of zeros and a couple of poles, that's exactly what I can mimic very, very easily with an analog circuit just using simple RCs. They're small, they don't really cost me any extra power, they can get me large time constants, and they can really basically do the same job I would have done if I just attempted to do some super long DFE or other structure to get rid of all this kind of long tail type of history. So with that kind of in mind, I think there's a few sort of key challenges that we see in terms of how you really get these types of approaches up into the 56 to 112 gigabit per second per lane type of generation. The first is just, as I said, the process technologies really are not helping us very much anymore. And so you have to be very, very, let's say, aggressive about essentially optimizing what circuit architectures you use to get up to these required gain bandwidths. The other one, which is fairly clearly an issue, is just actually closing the DFE loops at these speeds, because you just obviously don't have much time to really do it. And the final one, which I'm going to spend a little bit of time on, is if you actually want to stick with the analog mixed signal architecture, really realizing efficient analog feed-forward equalizers is not the most obvious thing to do. And there's a few, I think, kind of key techniques that have been that people have worked on over the last couple of years that I think really can solve this problem quite nicely. So the first one, which is really just all about gain bandwidth, and to kind of motivate why I think this is an issue, again, if you just kind of rip open, like the papers and publications people have made about various SerDes architectures that they've built recently, if you just kind of track through the signal chain, let's say from the input all the way out to either where the real decisions are made, or even in the case of the ADC, you're typically talking about maybe 4 to perhaps even up to about 8 stages of amplifiers that are kind of all sitting before you really get into the digital domain. So if you think about that, there's sort of like an implied bandwidth you have to maintain through that signal chain to make sure you have sufficiently low impact on your signal-to-noise ratio, and in particular not introducing extra ISI as well. So even if you include decision feedback equalization, which allows you to just get rid of some of the SI and mostly just care about how big your signal level is, roughly speaking, kind of the overall required bandwidth you need through that entire chain is about the symbol rate divided by 3. Okay, that's kind of the rule of thumb you should keep in the back of your head. So now if I've got, say, 4 to 8 stages of these amplifiers, that means that I need about 40 to 60 gigahertz bandwidth for each stage. Because obviously the more stages you have, the lower the net bandwidth through the entire cascade will end up being. Well, even in these most modern process technologies, if you're really using kind of simple resistor-loaded stages, forget even about just sort of like what the nominal power component would be, kind of like the CVF part of it. The part where you start looking at how fast are you relative to your own process technology can really start, kind of really hurting you here. Because at 40 to 60 gigahertz bandwidth with, about a factor of 2 or so of gain on each stage, now you're looking at like 120 gig or so. Well, that's pretty close to kind of like the intrinsic device speeds of many of the things that we're looking at. And so just that penalty you pay for getting up close to the intrinsic operating speed of the transistors can really start hurting you here. So obviously, if I've spent this much time kind of harping on why this is a problem, I've got at least one trick in my bag that I'm going to expose here, which is not my trick, by the way. This is actually something that was published about 12 years ago or so now, and in fact, it's been used in many different contexts and actually has a few different names because of that. But the basic idea is to essentially say that, look, if we're really interested in kind of being the most efficient we can in generating a certain size signal in a certain size time, it's very clear that essentially just taking some current and dumping that onto resistor loads is not the efficient way to do that, okay? And in particular, kind of almost the most efficient way you can think of to do it would be to just say, look, if there's a certain amount of signal I want to generate within a certain amount of time, I should just take a current, dump that onto a capacitor for that full amount of time, and that's actually going to be the most efficient way to do things. And the intuition behind this is kind of straightforward. So let's imagine that we're going to generate the same size signal over the same window of time using this resistively loaded structure versus this quote-unquote current integration. Well, in the resistively loaded structure, at first you're actually going to get pretty sharp slew rate here. But at some point, you're literally just dumping current into a resistor to create a DC voltage, right? And that's obviously not very efficient because, right, like I could have taken that same current and actually pulled extra charge out of the cap. Okay, well, that's exactly what this current integration structure is doing. It's saying, look, let me just take exactly all of my current, have all of it flow into the output parasitic capacitance so that I can use actually much less current to get to the same voltage over the same period of time. So to give you a little bit kind of more mathematical basis on this, if you kind of work out what the equations and all this imply, there's really sort of 2 points where this is different. Okay, and I'm doing this now specifically in the high-speed links context. So if I look at how much current it takes in the continuous time, meaning the resistively loaded structure, basically I'm going to call this like n tau here. This is kind of like saying when I designed my amplifier in the first place, how many RC time constants do I give that amplifier to actually settle within a bit period? Okay, and a typical number most people shoot for is about 3, because that sort of gives you like something like a little bit less than 5 or 6% of residual error from one symbol to the next. Okay, if I then work out how much current it takes me to build the current integration structure, there's kind of 2 points where this is different. The first is that n tau disappears from the numerator. Okay, so just like straight up from an efficiency standpoint, I already gained that factor of 3. But in fact, perhaps even more importantly, especially as we push these edges of the data rate, this term in the denominator over here, notice I have this n tau like of extra kind of bandwidth I have to implement that just kind of completely goes away on the bottom. So this is kind of telling you that like it's almost as if you got transistors that were like quote unquote 3x better than you had in terms of what the intrinsic speed limit they're operating at is. And again, if you're really getting close to that intrinsic speed limit, just getting rid of that term oftentimes is actually the biggest difference in terms of saving yourself a substantial amount of energy in implementing these very high throughput, very sort of, let's say reasonably long signal chains. So just to give you an idea of, sort of specifically how one might use this in practice, this is a particular sort of combined CTLE and 2-to-1 demultiplexing circuit that we used in the specific SerDes that I'm going to tell you about a little bit later, where basically we just take the inputs. This whole input stage just looks a lot like the classic continuous time linear equalizer you're probably used to, right? So just, current source is split, source to generation, input pair. And then all we're doing is we're essentially saying we're going to use this cascode devices in the precharge to either route this integrated sort of output to one side or to the other. And you can kind of see the waveforms over here, right? So for one half of the waveform, we route out, for example, to the Vout E, and then essentially are using this integrated voltage. And then in the other half, we're integrating out to the Vout O and using that integrated voltage. Now you may be looking at this and saying, well, like, aren't you also actually integrating the input too? Like, are you sure you want to do that? Don't worry, I'm going to show you a little bit later why it is that I actually explicitly do want to integrate the input. That I have, there's a method behind the madness here. Okay, so now that we've talked a little bit about just some of the lower level circuit techniques to improve our overall essentially efficiency in realizing the required gain bandwidth, the next thing I want to talk a little bit about is just how we go about actually closing the very tight timing loop that we have for the decision feedback equalizer. So as hopefully most of you are already familiar, right, this is a really nasty problem because basically you have to do essentially take whatever the small input analog voltage is, regenerate it up sufficiently that it now looks like a digital thing, because at the end of the day, a decision just means that you have a digital quantity rather than an analog one. Scale that back by some amount and subtract it off from essentially your next bit, all within that 1 bit period, right? And so if you're thinking of this, in the 56, 112 gig, this means you've got something like, 10 to 20 picoseconds for all of this stuff in your absolute worst case conditions, right? Definitely very, very tough. So kind of through most of the quote-unquote golden age, it turns out that what most people did is a so-called loop unrolling approach, where they basically said, all right, well, I only have NRZ, so there's really only 2 options, right? Either the previous bit was a 1 or the previous bit was a -1, quote-unquote 0. And so let me just speculatively kind of, compute both possible results, and then after the fact, select which one of them is actually the correct one. And the main benefit here is just that, it's not that you get rid of the feedback loop. Feedback loop always has to be there. It's just that you essentially push that feedback loop fully into the digital domain where you don't have to worry about amplifying up the small voltage, getting it back up to a real digital value. So that is indeed a good trick. It's been played for a long time. It really does indeed help kind of with essentially closing that timing of the first tap. But as you can kind of see on this picture here, if I actually want to do multiple taps of equalization, I actually can end up being the sort of overall critical path, because now there's this extra mux that you have to get through, that still also has to do all of the analog amplification to really make it all the way back for this next tap. And you can say, well, okay, maybe I'll like unroll one more time and so on and so forth. And yes, you can keep playing those games, but in case it isn't obvious, your complexity kind of grows exponentially with the number of taps that you're dealing with. And it grows by another sort of exponential factor if you're doing this in a PAM4 versus NRZ design. So, at some point, this definitely runs out of steam. So the key idea that some of my students and myself worked on I guess this is about 6 years ago now, is to essentially say, all right, let's take a step back and think really hard about what is it that the DFE is actually trying to do, okay? And so as we said before, the key idea with DFE is that you're trying to take something that looked like a quote-unquote analog input and then get it out to being a digital thing at the output. So what does being digital actually mean? Well, being digital means that you have some quote-unquote noise margin. In other words, that you can move around that analog voltage, and the interpretation of it in the circuit afterwards really does not change very substantially, okay? So the idea here is that if we say, well, look, if this thing that's doing the feedback based off of the output of this first stage, if you get the voltage to be large enough that that feedback device is essentially clipping, meaning interpreting it such that small analog variations really don't make an impact on its output, then you've actually achieved the behavior of a so-called DFE. So if you kind of notice my description, there was nothing that intrinsically said that I actually need a lot of gain in the structure that goes from the quote-unquote analog domain to the quote-unquote digital domain. It's just all a question of how big is the signal compared to where the slicing or let's say the clipping thresholds of that feedback device actually sit. Okay? So if you really start kind of poking down a little bit further into this, what this really basically says is that, okay, like I need enough overdrive on this input device here so that with the ISI that's going to remain having not been canceled yet, I still interpret things linearly here because I haven't actually done the subtraction yet, but that I get then enough swing at the output over there to really clip the next stage. Turns out you really only need about a factor of 2 or so of gain in this stage right here to kind of make all that work out. And factor of 2 is way, way lower than what people typically operate with, right? Typically, people are putting gains of tens or even hundreds inside of there, with obviously positive feedback type structures, but that does not turn out to actually be required. So point of all this is just to say that if I can drop the amount of gain I need in that stage, well, obviously the lower gain bandwidth I need, the less power it's going to cost me to actually implement that. And indeed, if you sort of go pull open the paper, you'll see that in 65 nanometer, we're able to actually just fully close this loop at well past 60 gigabits per second. And this was with multi-tap DFEs as well. So the next thing I want to spend a little bit of time on is just how things look in terms of the receive feed-forward equalizer. And so first I want to just focus on relatively short feed-forward equalizer. So let's assume that we're kind of again in this pseudo golden age type of architecture where nearby post cursors are largely handled by the DFE. There's a long tail CTLE, and the job of the FFE is mostly to deal with precursor types of ISI. So the reason why it's important to say that this is relatively short is that if you really start looking at these things, if you want to build a very long feed-forward equalizer, the first thing you would actually worry about is just what happens with these delay elements. Because if you have a long equalizer, you have many of these delay elements, and that's where actually most of your errors and other issues will come from. So for now, let's assume that that's not actually the problem. Like if I've only got like 2 or 3 of these, then you can kind of live with whatever errors are there. So if I'm in this design regime, the key challenge is really actually how do you implement this variable gain? Now you may think, well, like variable gain, like that's, that should be really easy. Like, don't I do these things all the time? Well, this is where you have to like peel the onion a little bit more and start thinking very carefully about what's really going to happen. Okay? So I'm just going to draw kind of 2 common approaches that people often will take for building these variable gain structures. The first one on the left over here is just to say, all right, I just have some fairly simple, let's say GM stage. In this case, I'm drawing it as being current integrating, but you can pretend the top is just resistor loads if that still messes with your head. But the approach that I'm going to take to vary the gain is just to essentially vary the bias current of this whole structure, right? Idea being that, if I drop the bias current, then, for a fixed resistor load, I'll have less GM, and therefore I'll have less gain. Well, the problem with this is that, unfortunately, as you drop that bias current, you're also dropping the overdrive of the transistors. And so obviously, if you want especially low gain, that means those transistors are going to clip much, much earlier. So just from a pure linearity standpoint, you start running into these issues where you have a bunch of stages that are supposed to be relatively low gain, but they all clip, and so the whole structure just doesn't behave as the feed-forward equalizer you really intended it to. The other approach, which conceptually is more quote-unquote correct, would be to say, all right, well, instead of that, let me just have a fixed bias that I feed into sort of each one of these like little unit cells, but let me build my overall transconductance out of a whole bunch of these unit cells, and then just select how many of the units I actually turn on to get any particular desired value of gain. Okay? So again, conceptually this all looks right, but this turns out to break like one of my, I don't know, I keep using golden, so maybe I shouldn't, but one of my quote-unquote golden rules that I usually tell all my students, which is, the thing you got wrong here is that you put the dynamic range on the signal path. Okay, so what do I mean by this? Well, if I'm going to go and build an FFE, I probably want anywhere from, I don't know, 5 to maybe even 8 bits of control in terms of what the actual value of the gain will be. And let's take 8 as being as being the example here. Well, if I really need 8 bits of control, that implies I'm going to have 256 of these unit elements. Okay? Well, the problem with that is that at some point, my unit elements are going to hit the absolute minimum size I can actually draw. And it often turns out that 256 times that minimum size is much larger than the width I actually would have wanted because of my gain bandwidth considerations in the first place. So what this is basically saying is that now, because of the range of gain you were trying to implement in this structure, you're actually going to pay a lot more power just because of the range of gain and not because of the actual signal path gain bandwidth you really wanted to implement. Okay? And that's bad. And this is especially bad when you start building complex equalizers because the more taps you have, the more dynamic range you need in terms of gain control. And so kind of like this whole thing just falls off the cliff very quickly if you're not careful. So again, one of these things where, if you remember nothing else, like this little moniker of keep dynamic range off the signal path, very important, very critical, and this will be true regardless of what kind of, design you're building. Okay, so again, if I'm harping on this so much, I obviously have an approach that I'm going to suggest as to being the alternative. And this is one of these things where you look at it and you're like, wow, this is like really a hack, but the hack actually just works beautifully and solves these problems. So let me go ahead and explain what it is that we're going to do. So the idea of the approach here is to say, all right, let's indeed take a fixed bias into some just, simple differential GM structure. So that will largely fix what the overdrive and therefore linearity characteristics of the structure will be. And the way I'm actually going to modulate the gain is instead of really changing anything inside of here, we're just going to add another cascode sitting on top, and we're going to modulate the gate bias of those cascode devices. So usually when people first kind of look at this, like, how in the world does this modulate the gain? Well, the thing to remember is that, all these transistors obviously have finite output resistance associated with them. And it turns out that when you include that finite output resistance, some of the differential current, will indeed actually flow into the cascode, but some of it will flow back into the output resistance of the input devices. And so the smaller you make that output resistance relative to essentially the GM of the cascode looking above it, the more will flow back and essentially not give you any differential current flowing into the output. So why is this really cool? Well, basically as I drop this bias, I'm going to drop the RO of the input devices. So I'll be stealing some of the differential current away, which obviously will reduce the gain. But from a linearity standpoint, I'm still mostly limited by just what the overdrive of the input devices was in the first place. And that I'm actually not modulating at all. So as you can kind of see in this plot here, which, this is actually a simulation, but, don't take it too literally because, arbitrary process and all that. What's happening here is that we're just showing as we tune this gate bias of the cascode voltage, in high gain versus low gain, visually you can see indeed these are both quite linear curves. Whereas if what I attempted to do instead was, just modulate this tail current bias, you can see that, for this low gain setting, once you get past, actually pretty low, value of the input swing, it's now actually clipping off and really just not behaving the way you intended it to. So as I said, this is one of these things where this is now exploiting a second order effect and something you wouldn't have thought would be an important way to go about things. But it just, again, it pulls the dynamic range off of the signal path. It allows you to modulate the gain kind of almost, it's not really truly arbitrarily, but over a pretty wide range. We've done 7 to 8 bits pretty routinely here and just, does not have any implication whatsoever on extra parasitics on the main high-speed signal path. Okay, so the next question that may come up is, all right, so maybe I've convinced you, or hopefully I've convinced you that if you want to actually build the VGA side of it, this is a very reasonable approach to take. The next question you might ask is, well, what if I actually do really want to build a long feed-forward equalizer? And so here, as I mentioned before, the key issue mostly comes back to how do you actually build that analog delay line? Okay. And the problem there is, there's lots and lots of ways one could imagine to build a delay line, but let's take the simplest approach and kind of see what the issue may be, right? So let's assume that I just did something really silly like this, where I just have a pair of switches to activate my sample and hold, And then I'm aware that, like, I'm going to be losing signal throughout this, so I'll just add like some simple buffer in between each stage so that I don't, get hurt too badly by that. Well, every single one of those stages is going to add some amount of KT over C noise, right? And to zero order, if you just kind of work out, rough, typical signal swings, voltage margins and things like that, it's going to take you about 10 to 20 femtofarads per stage for about 10 to 20 taps to kind of hit all of those constraints simultaneously. And if you remember kind of the numbers I was quoting before about, like how big flops are and how much power this all takes, 10 to 20 of these 10 to 20 femtofarad caps actually adds up pretty quickly, okay? Now, equally importantly, any deterministic error you make in these delay lines is also going to accumulate, right? And so in particular, if you're not really careful, any small little offset you inject from having done the sampling operation, by the time you're like 10 or 20 stages deep, the whole thing's probably railed out, and then yeah, you can go and like add offset cancellation to each stage, but by the way, that's a pain in the butt too, because you can't even tell the difference between that and like your gain setting. So this whole thing just becomes a mess very, very quickly if you try and go down this route. So instead, it turns out that, I think the real solution here is very much what we pointed at back when we started talking about how to improve some of the digital implementations, which is really parallelism, okay? So the basic idea here, which again, this is actually a pretty old one. I think this is the first sort of point I found this used in the high-speed links context. This is a paper from James Jousey at Intel in JSC 2005. The idea here is the following. Imagine I just take my analog input, and essentially I sample it with a parallel bank of samplers, but the clocks for each one of those samplers are essentially delayed by 1 UI relative to each other. So kind of this whole structure that's kind of sitting in the middle here, you can think of it just being one analog deserializer, right? And by the way, again, small side note, this kind of structure almost always exists in all of the ADC-based implementations because there's no one, sort of sub-interleaved ADC that's actually running at the full data rate. So you have to do this analog deserialization to make those work too. Well, once you've done that, if you kind of think about it, once I've done this one sample and hold operation where I have the thing on only for 1 UI and then it's holding it for another 2, well, after 2 UI, guess what? It's exactly created a delay by 2 UI in this case. So now let's say I want a delay of like 20 UI or something like that. Well, I could just build 20 of these things instead of just 3. And after I've held it long enough, I've actually created exactly the delay that I intended. But notice, I've done it with only one sampling switch in the signal path, not with n. Right? Now, it does mean that I have n copies of various delayed versions of the signal. So I'm going to have to take those n copies and kind of interpret them at the right times with the right gains to create the appropriate equalization coefficients. Right? So as an example here, and this is kind of why this is structured this way, say I have like this 3-tap feed-forward equalizer. C0 indicates kind of like the quote-unquote cursor, which is the one that would be grabbing this input at the time that phi 0 is on. C1 is indicating the thing that happened 1 bit ago. Well, if you think about it, phi 2 sort of sampled 1 bit ago relative to phi 0, so that's why that's going into here. And then similarly, C1 in this case is actually, C2 in this case is actually coming from phi 2 because that's the thing that happened 2 UI ago. Okay? So the whole idea here is that basically I'm just getting parallel data streams where each one of those data streams is delayed by a different amount of UI depending upon which clock phase it is that you actually happen to be operating in at that moment. So this is indeed a pretty powerful technique because, in terms of accumulating errors, I do this whole thing in one stage, right? So like as long as I can get one sample and hold to be reasonable, now I'm actually in reasonably good shape. The only sort of downside of this particular approach is that, notice I basically end up having to copy the equalizer gain coefficients, in this case 3 times, in general it's like n times. And so if I really have to do like a lot of delay and a lot of copies of these equalizers, essentially the wire array that you end up building over here can become quite physically long and therefore cost you just a decent amount of power to drive all the signals into it. And so that's the only thing you have to be a little bit careful about. Once again, if this is something I'm pointing out, then I likely have a trick in my bag that I'm going to point you to try and avoid it. In this particular case, the way that you can actually get around this is to build what I'm going to call a so-called switching matrix architecture. So this is where you have to buckle up a little bit. Just bear with me. I'll explain kind of how this thing is working. So everything over here on the left is the same as it was before. It's really just an analog deserializer. Okay? The only extra trick that we're going to play is we're going to say, look, I only want to build, in this case, 3 equalization coefficients. Right? Just the C0, just the C1, and just the C2. Okay? So I don't want to replicate those because I don't want the whole structure to be physically too large. So what this whole thing in the middle is doing, which you can see has 3 squared or 9 total switches in it, is it's really just acting like serializers that take each of these 3 deserialized streams and then are recreating 3 serial streams that have the appropriate delays on them. Okay, so how do you do that? Well, if you sort of think about it, when this phi 0 switches on, as we said before, this is now like the current thing, right? So the current thing should end up at the C0 gain weight. Well, for the C1 gain weight, that's the one that was 1 bit ago, and as we said, that's what phi 2 should be, and so that's why I sort of select that one when phi 0 is high. Similarly, the thing that was 2 UI ago, that's the C2 over here, and when phi 0 is high, I know that that's this middle tap right here. So if you just kind of walk through this, you'll see this kind of like this rotating structure. That's why we kind of called it the switching matrix, right? That also has, like if the deserialization is by n, it has n squared elements. Again, that's why we call it this matrix. But basically, really all you're doing is just picking off which one of the parallel streams you feed into the gain coefficient to just recreate the full rate output, but using a smaller number of gain structures overall than the fully parallelized implementation. Okay? And again, the only real advantage of this is just that you avoid the potentially large wiring overhead from really building all these parallel copies of the gain weights. So if you're interested, there's a lot more description of this. So one of my students did this back in 2014. This was done in the context of essentially a millimeter wave baseband, but was also operating multiple gigasamples per second. If I remember correctly, that one was done with the equivalent of about a 16 sort of UI kind of delay structure. At IC a little over a year ago, this was in 2018. I don't remember the exact number, but this is like what I would always colloquially refer to as the super crazy equalizer, because they had like hundreds of these feed-forward taps, thousands of decision feedback taps, very much using these kind of techniques that we've been talking about here, both in terms of the switching matrix to do the very large, essentially feed-forward delays, as well as some of these kernel integration and other tricks to do the very long decision feedback summation structures. Okay, so the next thing I want to say a little bit about is, now we've kind of walked through the equalizer circuits and, some more details on those architectures within those. I want to say some more on the clocking and CDR side of things as well. So again, if you kind of go back to that slide where I said, there was this quote-unquote golden architecture, almost everybody was using these so-called dual loop approaches in that case. So what do I mean by dual loop? Well, essentially the key idea with dual loop, which has been around for quite a while now, is to essentially say that, look, I want to be able to decouple the bandwidth of my CDR loop from the bandwidth of the actual clock generation loop. And the advantage here is that if my clock generation loop, from whatever reason, for example, wants to have a higher bandwidth, this is particularly true if my oscillator is relatively noisy, then by doing this decoupling, I can actually set my PLL bandwidth to whatever it wants to be to get the optimum noise out of that. And then separately set my CDR loop bandwidth to actually match with what's required based on the characteristics of the data and the channel and the standards and so on and so forth. And it just turns out that oftentimes the bandwidth you want in this loop for the clock recovery is, can indeed be much lower than what you want out of the PLL, simply because of the fact that, in the clock recovery case, your quote-unquote reference is relatively noisy, so you don't really want to track that too much. Whereas over here, your reference might actually be quite a bit cleaner than your oscillator is. The other reason that I think this became very much the standard was that, this kind of enables you to do tricks like essentially, build one really nice, good PLL kind of in the middle of a whole bunch of lanes, then distribute that clock out, right? And then locally at each lane, actually do the clock recovery that you need to recover that data, right? And if your PLLs are big and or power hungry, amortizing them across multiple lanes indeed is a very appropriate thing to do. So again, obviously if I brought this up, I'm going to ask the question of, is this really still the right way to go about things? And I'm going to argue that kind of both of these motivations, meaning specifically decoupling of CDR loop bandwidth from clock generation loop bandwidth, as well as amortizing especially the area of the PLL, I think are much less clear when we really get up into these 56 plus gigabit per second kind of generations. So why do I say this? Well, first of all, if you really want to be efficient and you really want to kind of hit kind of these data rates, you probably are going to end up having to build an LCPLL. And if I'm building an LCPLL, like the requirement on really having a very high loop bandwidth in that clock generation part is nowhere near as obvious, right? Because the LCPLL at a high frequency is probably much cleaner than your reference is. The other one, which is kind of very practical, but I think worth noting, is that if I'm at these 56, 112 gigabaud kind of things, I probably don't really want to be shipping around a 28 plus gigahertz clock all over my die. Because even if I can do it, I'm probably going to spend a decent amount of power just in that distribution network, and then perhaps like actually fixing all the errors I caused in my own distribution network. And so the argument I'm going to make here is that I think for these data rates, it's very likely you really actually want to move to a single loop design with a per lane LCPLL. Okay? So again, the single loop design, I'm going to argue that, from a CDR loop bandwidth standpoint, those loop bandwidths actually tend to be pretty close to probably what I wanted for the LCPLL anyways, and so I don't think that's as much of a penalty to pay. And similarly, in terms of the actual physical size of the PLL, when you're up at these clock frequencies, the inductors are basically tiny. Okay, they're typically way smaller than the size of the lane is in any case, and so the actual overhead of doing this tends to actually not be all that large. Okay, so then the next question is, do we continue with kind of this 2x oversampled CDR type of approach, or do we perhaps move to something slightly different? And as I said, in the golden architecture, 2x oversampling was by far kind of the most common way of doing things. The alternative, of course, is to say, well, hypothetically, from a quote-unquote Nyquist sampling standpoint, I should really only need one sample for every single bit, because, relative to the Nyquist frequency, that's already actually 2x oversampled. So can I actually get away with that? And that's the so-called Baud-rate CDR. So taking a step back, if we just kind of look at what hardware is required to implement the two, it's very obvious that there's extra stuff you actually would have to build to do the 2x oversampling, right? In the golden architecture, maybe it was relatively constrained. Maybe you just needed like one extra edge sampler and its associated deserializer, and you needed like a 4-phase clock generation. Whereas in the baud rate, you get rid of that extra edge and the deserializer, and you only need a differential clock. Turns out in ADC-based links, almost everybody goes uniformly with the baud rate approach. And I think this is not necessarily because they decided it was better. It was just, building another factor of 2 sampling rate on the ADCs is really super painful. So everyone just said, all right, well, screw it. We're just going to live with this, whether it works or not. I'm obviously being a little bit facetious. So to be clear, I do think actually baud rate is where you want to go. But there are some things you have to be careful about. So in particular, one of the ones you have to be most careful about is that the most common way of building these baud rate CDRs is what's called the Muller-Muller algorithm. Now, there's many different ways you can kind of write these equations, but under the hood, what they're really basically doing is they're locking to a clock phase where the value of the precursor ISI is equal to the value of the postcursor ISI. Okay? So for kind of reasonable channels, that's actually not a bad place to figure out as to where it is you actually want to do the sampling. However, you can kind of think about like corner cases that are pretty easy to come up with. So in particular, imagine that you had something that was actually like the front end for an optical link. And the optical link itself was, relatively clean. You had sufficiently high TIA bandwidth. You could get things that are looking almost like, square wave-like bits. Well, if I actually have a square wave bit, you can imagine that pretty much anywhere inside of this window, I'm going to have the same precursor ISI as I do postcursor ISI. So in classic, Murphy's Law kind of fashion, the implication of this will be that, you can go and try and build your Muller-Muller CDR, and it'll always lock at, exactly this edge or exactly that edge, because everywhere else it has absolutely no information. It doesn't know where else to go. And then you have this thing where there's a super clean channel, but now your CDR is giving you tons of errors, right? So the good news is this is relatively straightforward to take care of. And as I promised before, I was doing that quote unquote integrating front end for a reason. This is in fact exactly the reason you might want to do this. So if you imagine if I build a so-called integrate and reset front end, meaning that I just sort of over a period of one UI, I integrate whatever my input is, and then I deliver that as a sample to my output. If I sort of look at conceptually what voltage waveform would be coming out of that as I change which essentially exact analog phase I use to do that integration over, you'd end up with something that looks like this triangle wave, right? Because essentially only if you're exactly lining up the window with this full UI would you get the peak, and anything moving either to the right or to the left, you'll actually get less analog voltage coming out of it, okay? And so now, now if I actually apply something like a Muller-Muller algorithm, then indeed there would be a unique locking point. I'm going to claim, however, that Muller-Muller, this is obviously a dramatically simplified picture. I'm still going to have, somewhat more arbitrary waveform shapes that I might need to deal with, and those arbitrary shapes may indeed have similar issues. So what we're going to do in a moment is we're going to come up with a slightly different baud rate recovery algorithm that I'm going to show you, I believe, is actually more robust to these waveform sort of types of variations. But just to be absolutely clear, again, what I'm saying here is it's not that I have a literal waveform that looks like this anywhere in my signal chain. It's just that conceptually, as I'm sliding that integration window relative to my bit period, that's where if I then plotted, on the x-axis is kind of like my relative sample position, and y is the analog sample that came out given that position, that's where you get this triangular looking waveform. And so to be clear, if you just take that CTLE structure I showed you before, really there's no actually extra hardware required whatsoever to do this, right? And remember, I wanted that CTLE to kind of use current integration because that was a more efficient just way to build the structure in the first place. So it turns out this is kind of like an additional freebie that I get, and that's going to enable me to be more robust to the analog characteristics of the input waveform and the specific details of the channel in terms of finding the right locking position. So if instead of essentially, sort of looking at some balance between precursor and postcursor ISI, if instead of using that as my metric for where I'm going to place my sampling position, I obviously have to come up with some other metric, okay? And so the most direct metric one could imagine is to say, all right, well, let me just look for the point that really is the highest voltage that I get coming out of my front end. In other words, specifically, let me try and estimate the amplitude of my cursor and lock my sampling position to be at that point, okay? Well, it turns out you almost always have some loop that's actually finding that point for you anyways, because that loop is the one that you typically use to set your reference level against. And either, you either do it as I've indicated here, which is find the value of the level and then make error comparisons against that, or you sort of flip this thing around and essentially there's some level that you compare against to set the gain of your front end and essentially end up, that reference level is kind of like the thing that drives your AGC, okay? What you can see here, and this is an actual hardware measurement, indeed, if I just looked at the output of my so-called, DLEV or my error tracking loop, my level tracking loop, you can indeed very easily see that there's kind of a unique peak that you would find as a function of which phase you're sitting at relative to the incoming data. So kind of a naive way to make use of this particular metric in terms of closing the overall CDR loop would be to say something like, okay, well, let me start out at some particular timing, say P0 over here, some nominal phase. Let me essentially measure what data level I actually get, meaning what amplitude of the cursor I actually get. Let me adjust my phase by one tick, in this case moving it to, for example, P1, and remeasure what that level actually is. If the level is higher, I should stay there and actually continue advancing in that direction. If it's not, I should go back and maybe check actually the other direction, right? As you can imagine, I could just kind of keep iterating on this process over and over and over again. Now, the problem is that if I literally try to do exactly what I'm describing here, the implication is that every time I move my phase position, I'd have to figure out what is the new actual value of the data level. And that data level, it's a feedback loop, so it has a finite bandwidth. So the implication is that now your CDR loop bandwidth would have to be dramatically lower than whatever your data loop tracking level bandwidth is. And that's obviously not ideal because, if one of these is only at, say, 50, 100 megahertz or something, and the other one is supposed to be, 10 to 20, getting that to actually work out is quite difficult. So instead what we do is, it turns out you don't really actually have to know exactly what the data level was at each one of these phase positions. You just have to know which direction you're going, okay? So in particular, if instead of actually figuring out, the data level really was, X millivolts versus Y millivolts, what we're instead going to do is say, look, if I moved in one particular direction, did the data level go up or did it go down? And I'm not really going to worry about how much. I'm just going to see which direction did it go. So as you can kind of see from this picture here, if I then just intentionally move myself around by some small phase amount, in other words, I intentionally insert some amount of dither, then what you can see is that relative to the data level, for example, if I see that moving myself later in time gives me on average positive errors, that implies the data level is actually going up. Similarly, if moving myself, let's say, down or earlier in time gives me negative errors, that implies I'm kind of on this positive edge of this triangle waveform. And obviously, if you go back to the other side, now where you're on the sort of, falling edge, then everything just gets reversed. So what this really essentially tells you is that you can essentially just look at a simple correlation between which direction did you move your phase position versus which direction is the data level error kind of coming back with. If you correlate those two, that'll basically tell you which direction you actually need to move your phase in order to find this peak point in the middle over here. So this is indeed the approach that that we took in this design that I'm going to show you a little bit more detail of a little bit later on. It's a second order loop because obviously at the end of the day, the oscillator may not have anything to do with the data rate coming into you. And the particular way we sort of built this phase dither, which is again just this process of moving around and checking which direction is better, was just by going in and essentially modulating the delay of the clock driver. So essentially we just have some sort of dither generation element that goes in and modulates the delay of the clock, and we also use to correlate against to essentially figure out our phase detector updates. Now, to give you a little bit more detail on the stuff you really have to be careful about here, when you actually physically go and implement these things, let's say you've got this PRBS thing that's generating the dither. as is perhaps obvious, the absolute delay it takes to get from you modulating the clock phase here to having that impact really show up all the way at the end of the analog front end is definitely very different than just, basically going through a wire and showing up at this phase detector, which is trying to do the correlation. So if you're not careful, because of this delay mismatch, you can end up essentially losing gain in your phase detector, which would once again limit your overall loop bandwidth. So as usual, as long as you know about this, there's a trick you can play to get rid of it. And the particular approach that we took here is to say, all right, well, we know these two things are going to be mismatched, so let's actually just build two different dither sequences or different dither generation circuits, and just be able to adjust the timing of one of them relative to the other, so that essentially, this dither 2, for example, if it's going all the way through the drive, the feed forward front end, and so on and so forth, by the time it arrives over here, we're just going to adjust its timing so that these two, the second dither sequence, which is the one we actually use for doing the correlation against, that those two are actually aligned with each other. And basically the way you can find this is you can essentially just measure essentially the gain of your CDR loop, and the higher the gain is, the better alignment you have. And so that's what you would use to really kind of adjust these relative timing positions between the two. So this is just showing you a picture of the overall CDR implementation. Nothing really too magical here, and I realize it's a little bit faint, so I'm sorry it's a little bit hard to see. But basically there's just an LC oscillator plus a resonant buffer. As we said before, the dither itself is realized by modulating the capacitance of the tank sitting at the output of the buffer. The only other sort of trick I want to mention here is that if you really want to get reasonably high loop bandwidth, a lot of times the latency of your proportional path is kind of the key thing to watch out for. And so here we just use sort of a simple analog summation circuit to allow us to do that analog proportional path at a very high rate so that the latency is almost never really an issue. But for the integral side, that's where you actually have some additional dynamic range. That's where you really have to keep track of things. Just like we said before, once you've got a certain number of bits, you want to move that to digital. That's indeed exactly why we do that here as well. Okay, so let me just quickly tell you a little bit about sort of the specific 60 nanometer, 65 nanometer, 60 gigabit per second design that made use of many of these techniques. So in terms of the overall architecture, this is again very, very reminiscent of what I called the golden age thing in the very beginning. So we just have a 3-tap feed-forward equalizer on the transmit side. On the receive side, we have a long-tail CTLE. It was that, again, sort of combined CTLE/deserialization structure. A 2-tap feed-forward equalizer using that cascode gain control technique, and a 3-tap decision feedback equalizer, where that first tap was, again, built sort of using this low-gain regenerative structure in the middle. And similarly, as I described previously, this is also all done with a single-loop Baud-rate CDR, and it happened to also include all the equalizer adaptation engine, just to prove that indeed all these things are working properly together. So this was published by my former student Jado Khan in JSC in December 2017. So just to give you an idea of kind of the overall test setup, actually I should have mentioned over here, so it was actually about a 0.7 meter, 32 gauge twin-ax cable that was used for all these experiments. To give you an idea of the test setup, basically we took the die and directly flipped it onto a PCB, and then had just short traces that went out, then soldered the cable onto the PCB on one side, and essentially symmetrically on the other side as well. So the particular test setup I'm showing you here is just to be able to test essentially simple things like the bathtub curve without necessarily the CDR being engaged. We'll see that, the CDR functionality a little bit more in one moment. So just to show you that indeed, this is a real link. It's actually operating, with a pretty poor response in terms of the channel that we're operating over. So here, this is kind of, the actual eye diagram without any equalization or anything like this. This is just going over the cable and essentially, sort of the board construction. And overall, this is about 21 dB loss at 30 gigahertz. So certainly not like, like the worst channel you've ever seen, but, this is a very reasonable amount of equalization to have to handle. The other thing, which is kind of a side note, but it turns out for many of these circuits that we're talking about here, the loss at Nyquist really is not kind of the thing that tells you how bad of a job you have in terms of equalizing. It's actually much more just how big is the ISI relative to your actual cursor. That really tells you a lot more about, in terms of designing the circuits, what are the things you have to actually, pay attention to. And so just to give you that number as well, there's about 3 times as much, amplitude of ISI as there is actually cursor amplitude in this particular channel. So if we then look at the sort of overall signaling path performance we got out of this, you can see now after equalization and everything, both on the even and the odd paths, we're getting nicely open eyes. These are all sort of measured with the on-chip, essentially SHMU capabilities that we had, just reusing the adaptive sampler. This is, however, without actually turning the CDR on. So this is kind of like with locked clocks on both sides. And as you can see, there's about, sort of from one end to the other, there's about 30% of a UI of margin at, I'm going to call it 10 to the minus 12 or so. This is a standard thing of, you don't really know what the bit error rate is, but you measure 10 to the 13 bits, and you say that with a reasonable confidence interval, that gives you about 10 to the minus 12 bit error rate. Okay, so now in terms of the CDR, because obviously we want to prove that that really works as well. So over here on the left is just showing you sort of a measurement taken of, okay, if we sort of statically hold the phases relative to each other and then sweep them, what do we see kind of in terms of the average output from the phase detector? So this is just showing you that indeed, on average, the phase detector is kind of giving you a negative gain and, sort of is lined up at the middle. This is just showing you that indeed the clocks come out aligned after the fact. And perhaps really much more importantly, we did a real jitter tolerance test as well. So at 10 to the minus 12 error rate, this is kind of the curve that you get. You can see we have a loop bandwidth of about 3 megahertz or so. And as corresponded to this picture back over here, I said there's about 30% margin. Indeed, at high frequencies, that's exactly the 30% margin you see right there. So to give you a little bit of a sort of overall power breakdown here, if we look now at sort of both the transmitter and the receiver, so on the transmit side, which to be clear is definitely not where we're focusing, but basically we just made sure everything worked. It's about 152 milliwatts or so. It's kind of interesting to see where all these things went. So in terms of the oscillator, just the clock drivers, the dividers, about 50 or so milliwatts, about 30% is being spent on the clocking. About another little bit more than 30% is actually being spent just on the actual TXFFE and its associated serializer, right? And this is the stuff that's really running at high rate, so it kind of makes sense that that burns a decent amount of power. And then just sort of peripheral things like, dividers you need to keep, the PLLs locked, various forms of deserialization, PRBS generation. That's kind of about where the rest of the power is going. On the receive side, again, it's kind of interesting to look at where power is really being spent. Kind of all the complex signal processing we were doing. So all the CTLE, all the receive feed forward equalization, all the DFE, all that stuff was only 46 milliwatts, right? So about 30% or so, right? So this is really telling you if you actually kind of push very hard on the circuits, indeed you can actually get things to be very efficient. And I want to remind you, this is in 65 nanometer, okay? So, from most of our perspectives these days, like super ancient process, right? Having said that, just building the clocks and driving them, even with the resonant structures, indeed will cost you some power. So that, cost us about 55 milliwatts or so here. And then again, peripheral stuff like, dividers that you need for keeping everything locked, the deserialization, the CDR adaptation, that's kind of where all the rest of the power is going. But you can see the receiver is actually, even a bit more energy efficient than the transmitter is. So on the whole, this puts us at about 288 milliwatts for that 60 gigabit per second, NRZ design. So a little bit under 5 picojoules per bit, again, in a 65 nanometer CMOS process. So just to kind of wrap things up a little bit before I open it up for some questions. As I said from the very beginning, regardless of which way you go about it, if you want to keep going down this marching path of increasing the data rates, continuously by about a factor of 2 every 4 years or so, the answer is always going to be the same, that we have to absolutely improve the energy efficiency because, power budget doesn't go up, throughput goes up, picojoules per bit has to come down. There's no way around that math. The next kind of key point that I really hoped, sort of you will take away from this is that, there is good reason to actually use analog mixed signal circuits kind of across the board, even if you're really doing an ADC, quote unquote, DSP-based implementation. And that's really because, again, when the dynamic range is relatively low, meaning that when you build the analog circuit, you're not actually adding any extra parasitic capacitance or any capacitance in to try and reduce the noise. It's just it already gives you low enough noise. Then that's very likely going to be a candidate where doing it in an analog mixed signal domain is going to cost you less than building the digital equivalent. And again, as a reminder, sort of the main source of essentially dynamic range in links is really just kind of the channel itself, right? And so even with 40 dB, you're still only looking at about 6.5 bits or so. Now you might say, oh, but like, I did like PAM4, okay, fine. Like it's an extra bit. Yes, an extra bit maybe is enough to cross you across that threshold. But if you put CTLE in, you can actually knock a few dB off of this. And so again, not so clear that, it's a very obvious win for really moving all this processing into the digital domain. So kind of the point of all this is that, again, I think kind of regardless of which particular implementation approach you're taking, I think, really being cognizant of these mixed signal techniques and really kind of pushing them, to kind of be as efficient as you can is absolutely going to be a worthwhile endeavor. So, well, what are the keys to really getting these mixed signal circuits to be efficient? Well, first of all, as I kind of harped on a few times, you want to stay away from that intrinsic device speed limit. Now, sometimes, just the spec says that you have to have a certain amount of gain bandwidth. Well, as I showed you, there's a few circuit techniques we can use to try and get around even that, right? So things like current integration, and invoking the appropriate forms of parallelism in the right place, paying really careful attention to what signal processing function you're actually trying to build and what it really requires in terms of gain bandwidth. This is the example of pulling the gain outside of the DFE loop. These are all the sort of flavor of techniques that I think fall in the same general category of, just keep away as much as possible from the intrinsic speed limit of the devices. The other one is kind of, this tagline that I told you before, which is keep dynamic range off of the signal path, right? And especially DC dynamic range, right? So anything where it's, there's something that's relatively constant and relatively slow, but forces you to start making everything bigger and more power on the signal path, that's probably a good candidate to rethink the way you actually built that circuit. Because in my experience, there's almost always a way to sort of pull that particular function out off to the side and do it in a way that doesn't really force you to burn more power on the critical high-speed signal path. So yeah, so I think that's what I've got, and I'm happy to open up for any questions.
So questions? If you could repeat the question.
Yes, of course. I'm standing between everybody and dinner, so.
So I think most of the recent PAM4 SerDes links, we've seen the trend has been that there is still a significant amount of analog front end. It's followed by the ADC, DSP, which is fairly large number of XOP tabs.
Yep.
Single DSP tab. And then the argument there mostly comes down to we need to be much more precise in ISI cancellation. So PAM4 is more sensitive to the PAM4 in RZ. And I'm wondering if
do I buy that argument, I think is what you're going to, right? Yeah, so it's a great question. So just to repeat the question, if we sort of take a step back and look at, peel the hood under many of these recent implementations on PAM4, almost all of them look like a fairly long feed-forward equalizer, typically implemented in the digital domain. And the argument that's typically made is that, well, because this is now a PAM4 link, you basically have, you need to be 3 times more precise in terms of the ISI cancellation as well. Now, by the way, side note, you're doing FEC, so they're not really that precise either, but we'll ignore that for the moment. And so the question I think kind of came down to, do I believe this as being a valid motivation for going down that approach? So thank you. That's perhaps I served it up well enough that that the answer is clear. No, I don't buy that at all. And I think the real answer there is just that unless you kind of know the right combination of things to do to build these analog, FFEs, quote unquote, the right way, they can indeed be very painful, right? And so I think if you don't sort of walk through that long list of issues, right, how you do the variable gain with maintaining linearity, how you pull that out of the signal path so you're not ending up paying penalty for that, how you do these relatively long FFE delays without, again, paying a huge amount of power for that, you have to kind of solve all of those issues. But I think you can actually solve all those issues, and then in terms of precision, that really just comes down to how many bits you have in that DAC that's off on the side on the cascode. So because it's going to be closed in an adaptive loop anyways. So I think all that can be done, but obviously that's not the current practice.
Okay, so you don't see fundamental.
Yeah, I don't see a fundamental reason for it. I think I think it's again one of these practical things where, again, unless you solve all that checkbox of problems, and then on top of that you really know how to build all those circuits in a way that will meet all these constraints, it's just easier to say, I know how to build an ADC. I'll build an ADC, and then the digital gates I'll verify with all the big hammer of digital verification I have.
Question on, I think slide 46. So you try to do the 2-bit method, right? So to master the delay. But that Victor circuit, is that the mimic of the path, or why don't we just use a normal programmable delay?
Oh, I see. So the trick there is that basically these dither circuits. Oh, I should repeat the question. Sorry. So the question was basically, we have these 2 kind of dither circuits that we've built here to try and match the delay between them. I'm going to paraphrase your question just a little bit, which is, how does that really work? Because, isn't it, for example, always going to be the case that there's much more delay on this path than there is on this path, since this is just a wire, right? So the short answer there is that these dither sequences are actually relatively short. So in our case, I believe this was a 7-bit repetition sequence, so a 2 to the 3 kind of PRBS. And so the trick that we play there is that since this is all running continuously, essentially just by seeding the dither sequences at different initial conditions, you can essentially kind of rack the delay over for things that actually would have been longer otherwise. So in other words, let's say I needed, let's say 10 UI of delay, because I only have a repetition of 7, that means that I can just do a 3 UI difference by seeding one relative to the other. And then things that are finer than that, that's what this phase interpolator is actually doing.
So programmable delay may not work.
It's said in a slightly different way. The programmable delay really just means different initial conditions for these two dither sequences. And then anything that's faster than the clock of the dither sequences, that's what you deal with using the PI. So the phase interpolator just needs to span over, like, basically in this case, these are running at like UI over 8. So that has to span over kind of like a UI over 8. It has, in our case, about 3 bits of resolution so that we can line things up to within about 1 UI. Yeah, it's a good question. Yeah?
Can I comment on the way to consider the P equations? How about the analog or the digital that cut off part thing?
Sorry, the question, can you repeat the question one more time?
I mean, when we consider the P equations, does it change the opening point?
Oh, I see. Got it. Okay. So the question was, if we consider things like process variations, does that, typically change whether or not you want to be in the digital domain versus the analog domain? Depends a lot on what exactly it is you're doing, but the short answer is, in my experience, no. Because, people like to make a lot of difference about, sort of why analog is so bad and it's so hard and all these other things. Most of the stuff that screws you in analog screws you in digital too, and so my opinion is that most of the time, if you know what you're doing and you're careful about those issues, it's kind of the same on both sides. Now, in detail, obviously, what I'm saying is not exactly true, but to zero order, I have not seen let's say from a conceptual standpoint, things that are really dramatically different between the two. So another question. Yeah?
Quick, could you please go to the slide on power consumption breakdown?
Sure.
So, just a basic question. Do you have more room for reducing the contribution from the clocking?
Oh, I see.
It's like 70 milliwatt from oscillator and drivers and the dividers.
Yeah, so the question was, do I think we have room to reduce the power consumption from the clocking? Absolutely yes. I'm not going to claim this is kind of the bottom of it. I would also mention, again, these were like running around 30 gigahertz clocks in 65 nanometer. Not that you can't do it, right? People have done much higher frequencies than that, but I think, even just sort of the relatively straightforward process scaling, even to like a 16 or something, would probably help quite a bit with some of that. Of course.
I have a follow-up question on that. So is it because, how much of it is because you're using one PLL for each clock recording rather than...
I see. So the question was, how much of this is coming from basically, one PLL for each lane as opposed to a more shared type of architecture? I don't remember the exact power breakdown. I think it was about, let's call it 50-50 or so between the buffer and the PLL itself. But I think the thing that I would point out is that, and this is kind of one of these, let's say, this is not as fundamental of an argument, but in practice what I typically see happening. A lot of times what happens is when you say, okay, I'm going to build this one shared PLL, then you start distributing it, and then the distribution has some non-ideality you don't like duty cycle distortion or other power supply induced jitter and things like this. And then you add, okay, so I'm going to add like a duty cycle corrector to fix that. And then, but that duty cycle corrector has not so great power supply rejection, so now I need to like build an even better regulator. So the point I'm getting at here is that a lot of times I see these things just snowball, where by the time you're actually done doing all of it, I think you just add enough other stuff that is on your high-speed signal path that you probably don't actually really win anything versus just building the one thing and living with it there. Yeah, again, not a fundamental argument, but I've seen that happen more than once. More questions?
Sure. If we go back to the beginning, where you made an assumption about the design landscape.
Okay.
And you had a highly optimistic estimate of what a stage in the CTL
Right here, I think, yes.
is going to be running at. So, as you just mentioned, there's stuff. And the stuff is, I need transistors big enough to match things. So therefore the capacitance is no longer only driven by...
I think you're violating my dynamic range on the signal path, but we'll get there in a second.
Okay, or current density limits or other such things. So typically for the speed that you're going to need to pass in that part of the chain, which is 20 gig-ish type number, you're running milliamps. And this is sort of what top down versus bottom up top down says it's always around milliamps, and there must be reasons. And bottom up says, well, gee, I should be able to do this with 2 fingers. It's obviously just going to move the balance point. But that's a pretty small number, so I'm thinking the balance point moves by like 12 dB.
Yeah, so I mean, let me attempt to rephrase your question and then see if I can come up with an answer for it. So the question was, in our experience, in my experience, I'm going to speak as you. We do sort of these lower level calculations, and we see that it should have been X milliwatts, and in reality it comes back as Y, and Y is always much larger than X, and it seems to be there's some integer factor between the two of them. And I think your question was going to come down to, well, like, if the ratio between Y and X is larger for analog than it is for digital, then that would move the balance point. I think that's where you're going. So absolutely yes, that's certainly true. Why it is that Y is different than X for digital versus analog, I think is then really the key question, because there's a lot of other X versus Y things that are going to happen in the digital domain just like they are in the analog domain. And I think this kind of touches on some of the discussion from earlier, which is just that I think there's a lot more general familiarity with how to sort of push things really hard on the digital side in terms of power optimization than there probably is in people really being very careful in all these ways on the analog side. And so I think just from a purely practical standpoint, if there is a difference between those ratios, I think that's where some of that is coming from. Again, non-scientific argument, but now we're getting into the non-scientific stuff. So
Digital is dynamic for the way people do it for most CMOS stuff. It's dynamic, which makes a big difference.
which, by the way, you can do the analog stuff that way too, but that's
We
yeah.
and some of those solutions, look a little better in terms of what their actual performance is, but that would go to the X not equal to Y for digital.
True, absolutely.
I'm sorry, the ratio of X.
Right. Correct.
Ratio for analog.
Correct. So it's just to repeat for the camera and for posterity. The point was that in digital you're largely operating in dynamic conditions, whereas classic analog you're obviously, as I've drawn here, classic class A type of things. And the side comment that I made was that, well, hey, maybe we should not be doing class A kind of things on the analog side, and that certainly will help as well.
More questions?
Yeah.
My question is on page or slide 43.
Sure. You guys are giving exercise to my fingers.
Yeah. How do you know that you are in rising slope or falling slope?
Okay. So the question was, how do we know if we're rising on the rising slope or the falling slope? You don't intrinsically know. You only know by looking at, if I move the dither, for example, to be my phase a little bit late, and then I just watch what happens to the output of my error slicer at that time. If on average my error slicer is saying that I have voltage that's above the level whenever I move in that direction, that means that I'm on this slope. Similarly, if let's say I do the same thing. Let's say I go a little bit later in time, but now I see that my error slicer is telling me your voltage on average is lower than the threshold, then that means that implies that you're on this falling slope. So that's it. That's the way you extract that information.
You are not one UI apart, is that right?
Oh, no, this picture is not necessarily one UI. In fact, the time axis is totally arbitrary here. So in reality, if you pay kind of very careful attention to what really happens here, and just for the sake of time, I didn't kind of go into this detail. What will happen, however, is that there will be ambiguity in exactly when you reach the peak, because basically that dither kind of creates almost like a deadband in some sense, right? Because you can imagine if I move to the left and move to the right relative to the peak, then now I actually can't really tell which direction I'm at. So the size of that dither definitely creates kind of a floor on the precision with which you can find the exact peak of that waveform. But once you're sort of outside of that, deadband, that's where, being on the positive or the negative side, that one is relatively clear. Yeah, it's a good question.
Was it for integrating format honestly relying on the gain peaking or anything?
Okay, so the question was, are we still relying on gain peaking and things like this? So the actual front end we used in that 65 nanometer design was pretty literally this. So it had the CTLE function inside of it, but there was no inductive peaking or anything of that nature. This is again one of these kind of just very practical things. And this is not going to be uniformly true for all data rates, so don't take this as being gospel. But even at this kind of 60 gigabaud per second rate or so, in our experience, if we were to attempt to go and add additional essentially peaking inductors inside of it, the extra parasitics we picked up, not even just from the peaking inductors themselves, but from the wires you'd need to just escape and get around those inductors, were probably sufficiently large that whatever benefit we would have gotten from power was kind of wiped out by just having that extra capacitance. And so it's, again, just one of these practical things where if the thing you insert to try and improve your power just makes all the wires sufficiently long, it may actually be a net loss at the end of the day. So in fact, I probably have it in the die photo, but the only inductors we had in that particular 65 nanometer design were associated with the clocking path, and that was it. You can't see it too well, but the sort of the core circuitry themselves were actually quite small. So yeah, there it is. So you see over there on the right, that's the equalizer. All that other stuff is, inductors, clocking, etc. So the equalizer was just super compact, exactly to try and keep the capacitors as small as we can. It's a good question.
Just related to that, you didn't have a track and hold before it integrated.
Nope, no track and hold before they integrate. Just integrates the input. Yeah, exactly. So if your question is, don't you quote unquote lose a little bit of signal that way? Yes, there's a fractional loss that you get from that. But the relative. So there's two things. One is I want to use current integration from a circuit standpoint, and so I can make up for gain actually much more than I would have lost from that, just by kind of bumping up the current there. And then two, I also explicitly wanted to get rid of the waveform dependence effect. Yeah, it's a good question.
What was the CDR bandwidth you reported? I thought
it was 3 megahertz. You can kind of
with all these techniques, if you wanted to do something more. Right?
Oh, I see. This is about where we were intending to get it for this particular one. The main trade-off with this particular structure, which is a very good question, by the way. The main question, or the main issue there, is kind of related to what I was saying before, which is essentially you can imagine the larger you make the dither step, the larger your CDR loop bandwidth would be, and then but obviously consequently, the more you're sort of paying just from losing that dither step size. So we optimized it for this particular point. You could optimize it for other points. That also depends a little bit on how much noise you're expecting on the way in. But we have done other designs, sort of up in the 10 megahertz range, and that seemed to be very feasible. If you want to be in like 50 plus megahertz, then that you probably don't want to go in that direction. Although, again, as a side note, most of the ADC FEC designs have also converged at right around 3 megahertz loop bandwidth for other reasons.
Yeah, but they have the latency. So
correct, they have a latency problem. So exactly. Correct. It's a different trade-off. The numbers happen to end up being about the same in this case. Yeah.
Any other questions?
Actually, in the previous session, I asked a question comparing the power consumption between the ABC base and the analog or mixed signal.
Yep.
Right? So we have a data point from 16 nanometer that's about 7 picojoule per bit for the ABC base. So I don't know, can you give a good estimate, like if you take this design to 16 nanometer, how much more?
Yeah, it's a great question. Some of this is going to get into what Eric was asking about before of, the industry design versus the academic design. We do actually check corners and everything like that. So, we're not skipping things, but, obviously we're not trying to build 1 million of these parts or even more than 10, right? So I think there's some integer factors we have to be careful about there, but I guess I will say, notice this is sub 5 picojoules per bit, at 60 gigabaud, not the same channel, not the same process technology, but, apples to apples, I think there's a reasonable shot. There's about at least a factor of 2 there, but, that's me kind of doing this.
Any other questions? All right, if no other questions, then let's thank you.
Thank you.